So in our last segment, we got to talk to Dave and learn a lot more about him and his history in the powder metallurgy industry and how he's been on the different sides of this business and, from being in the lab to being out in the floor and manufacturing and now in sales. This next segment, we're going to talk more detail about the powders, how they're manufactured, the differences in sizes, and what makes them unique compared to other materials. So enjoy this next segment and be sure to ask us any questions if you have them. Now, we're talking about these metal powders that are basically a little bit smaller than the diameter of one of our hairs, and that's the coarse side of it. And then it goes much finer than that.
Well, if you're talking about like HVF powders and that industry, you're right. But other processes use much coarser powders, of course.
Right. And that's the whole thing with distribution. So in thermal spray, we're very often in that 53 micron down to about 11 micron. So that 11 micron is less than half a thousandth of an inch in diameter. Yeah. So that's a pretty fine powder.
Very fine powder.
Yeah.
And when you're screening or when you're sizing those powders, you'll typically use conventional screens at the coarse end. And then when you get down to the finer ends, screens become fairly ineffective and inefficient anyway. If you can think about the analogy of like sifting something like sugar through a screen and then try to do that with flour, flour just sticks and plugs everything up. So we typically would use air classification to size something that fine and not use screens.
And what's air classification? How does that work?
So air classification is basically using the force of airflow against velocity to pull particles out of a stream.
So it's kind of like if I had talcum powder in my hands and I blow on it, the very fine light stuff's going to go up into a cloud, and the heavier stuff will stay in my hand. Right. So we use that same phenomena classifier, basically some kind of little cyclone that the lighter particles get carried with the stream of air and they go on, and the heavier stuff kind of drops out.
Right. And a cyclone is one of the main methods used for that. So it basically uses centrifugal force, and it blows an airstream through there, and the heavier stuff, which is going to have more centrifugal force, will stay in the cyclone, and the lighter stuff will get blown through to a secondary dust collector, typically a bag house where it's collected and it can be recycled.
So Dave, some of these powders end up being really fine.
Right.
How important is it how you store them?
Well, it is important that they're stored in obviously a hermetically sealed container. Mm-hmm. It's good to have it temperature controlled, because one of the things and I see this quite frequently, is when you have powder that's stored. You have to be a little bit careful, too, if you're going out into a very hot, humid environment, because if you've got powder that's stored in a very cool place, you take it out to a shop and it's, 95 degrees with high humidity, and you open that bottle up, you can get a lot of condensation that happens fairly quickly. So it's important to keep the powder dry and temperature controlled.
So I see guys have old refrigerators with a light bulb in them. Does that work?
It helps. It does help. That's a typical trick used for stored welding rod too. And they've taken a page from that. And it does work. It does help keep the humidity out of there. It's not the most ideal situation. I also see people with heaters on powder hoppers too. They sell little resistance heating kind of blankets that wrap around the powder hopper and keep it warm. Right. So that when you dump the powder in there, it doesn't get cooled off and get, condensation.
Right. So it's basically a relative humidity situation that the higher the temperature, the total moisture content out there is still there, but because it's a higher temperature, it holds less? Or do I have that backwards?
Yeah. Well, if it's a higher temperature, it won't condense. If the powder
won't condense.
If the temperature of the powder is below the dew point in the atmosphere, you can have condensation on the powder.
Correct. And that's the
flow well. Yeah.
Yeah, the liquid on there. So for iron-based alloys, that could be a real problem. Now you start rusting your iron. But for the other alloys, maybe it's not quite as sensitive. So if your powder does get damp, can you dry it out?
Yeah, you could dry it out by warming it back up again. You could put it in an oven like you described, but you could also put it in a more conventional. You don't need a lot of temperature. You just want to have it, obviously the boiling point of water is 212 Fahrenheit. If you get it above that, it's coming out for sure. But if you even have it close to that and give it some time, it will dry out. And people put them in bread pans and all kinds of things to dry them out before they put them back into the container.
Well, maybe I have a new application for my air fryer that I have over in the shop. I can use that to dry these powders out, huh?
Don't blow the powder around in there.
Oh, yeah, that's right. That'll happen with that.
Get on your pizza or something.
Okay, so let's switch gears a little bit. We wanted to talk a little bit about spray infused powders. So the spray part's pretty obvious. We take these powders and we put it into some type of torch where we melt them and we use some high pressure gases and we atomize it and we coat something with it. Then we go to what's called the fusing process. And that's done with a torch typically. So why don't you talk a little bit about what's the magic in the fusing process and what actually occurs when it fuses?
Well, I'm not sure if there's any real magic, but sometimes it seems that way. So what happens during fusing is a couple of things. First of all, when you initially spray the powder on there, although you are partially melting it, in typical flame spray, you're not melting it real thoroughly. You're just kind of getting it into its plastic range, and it's kind of just mechanically sticking to the part through, number one, the anchor pattern that you've established by grit blasting the part, and then the roughness of the surface of the powder sticking to itself. But if you were to cut and section that after flame spraying, you would see a fairly porous surface. That would have a very high density. And it's also really just mechanically bonded to that anchor pattern, that grit blasted surface. So in fusing, what you're doing is you're coming back and bringing that temperature of that powder back above its solidus temperature. So, these materials don't have a single melting point temperature. They have a melting range where they begin to melt at one temperature and become completely liquid at another. And during fusing, you're taking it into that plastic range where it's partially molten. So you're densifying the material. So all those holes are coming out. But the real magic is you're metallurgically bonding it. Most of these self-fluxing powders, as we call them in the industry, which are the spray infused powders, contain constituents such as boron, which is a very small and rapidly diffusing molecule, and that material diffuses into the surface of the substrate, causing a metallurgical bond to form, which is much higher than the initial mechanical bond.
Right. So that's a really important distinction. I'm going to talk a little bit about the diffusion too. This is actually these little atomic particles making their way into the base material and actually penetrating in. And if I have it correct, I think there's some outward diffusion and inward diffusion. Some of the constituents of the material that was on the surface is actually diffusing into the base material, and some of the base material is diffusing out into the coating. And then you get this zone in between that's totally different from anything.
Yeah, diffusion can happen both ways, but diffusion is mainly a function of the size of the molecule. So whatever has the smallest molecule is going to diffuse the fastest. So you're going to get a lot more diffusion of the coating into the substrate than of the substrate into the coating. Now, some substrates have quite a bit of carbon in them, and that's a pretty fast diffusing molecule also. So, but yeah, absolutely, diffusion can happen in both directions. And you can have different chemistry near the interface.
Another phenomenon with these spray infused powders is that they're very high hardness. What's generating the high hardness in these materials?
Well, that is generally true. And these same molecules that diffuse rapidly because they're small, they basically exist kind of interstitially in the metal, and that interstitial presence of those molecules causes a lot of stress, which causes the material to be hard. So the more boron and carbon you have in there, the harder it's going to be.
Right. For those technical people out there, what's happening is the dislocations are getting piled up and they can't move.
Yeah, and they can't move. So hardness is the result of that. And the other thing that I think is important to understand is the same constituents that cause the material to become harder also lower its melting point. So as you go up in hardness, you typically see a lower melting point. And so the harder stuff is generally easier to fuse, or at least it fuses at a lower temperature and much quicker, and it's easier to see.
Right. And I guess along the way, we'll probably have some carbides forming, some boron carbides and silicon carbide, and probably there's all kinds of wild chemistry going on inside these alloys, which is beyond what we want to talk about today, but it's just worth noting for the metallurgists out there who might be listening to us today.
Yep.
Let's see.
And this whole fusing process is really kind of like brazing. I mean, it's the same process as brazing, but it's just done on a surface as opposed to joining metal parts together.
So in brazing, are we getting some diffusion of that brazed alloy into the base material?
Absolutely. That is the mechanism that the braze bond, that basically forms the braze bond, the metallurgical bond in brazing.
Well, let's take it one step further. How does that compare to soldering then with lead?
It's pretty much the same exact thing. Brazing and soldering are only differentiated by a temperature. So of 500 C is what the official demarcation line between soldering and brazing is, and that's just based on alloy families. Your leads and your tins are below 500, and your nickels and your silvers and your coppers are above 500. So,
right.
But really, the process is exactly the same.
So, Dave, the common way that the spray and fuse alloys are put on is with a low velocity torch, whether it's a Metco 5P or you take the Teradyne torch, one of these torches, or the Volcomo torch. They're relatively low velocity, and you get quite a bit of processing in it. There are some people who spray these spray and fuse powders with HVOF to get the dense coating right off the bat. Does that help at all with saving material later on? Or what's the benefit of using HVOF to put a spray and fuse powder on?
Well, the benefit of using the HVF process to put those type of spray and fuse powders on is that you already have the density. I mean, HVF spray is a very dense coating.
Right.
In spray, you're densifying and metallurgically bonding. With HVOF sprayed coatings, you really only need to worry about the metallurgical bond part of it. So if you have a complex geometry part that has a tendency to maybe want to run or sag when you're trying to fuse it, because you have to, the lower the density, the higher liquid phase you have to get to densify it, right?
Got
and
it.
If it's already dense, you only need to really diffusion bond it. So you don't have to.
You could do it at a little bit lower temperature, and you don't have to get everything so liquidy. Yeah, liquidy. Yeah.
Right.
I think that's a metallurgical term, liquidy.
Liquidy, yeah, that would be it. Yeah.
Yeah.
Yeah, I mean, you can have parts run and sag. If you're trying to achieve full densification during fusing, and there's portions of the geometry where it's kind of upside down or vertical. Obviously,
yes.
The more the liquid phase you have present, the more gravity is going to act on it.
Right. So, is it an advantage if you're using furnace fusing, where you take all the parts and put them in a furnace instead of using a rosebud torch? Is it an advantage to use the HVOF to get the denser coating first, so you have a smaller temperature range you have to deal with?
Yes, particularly if you have a complex geometry part. Absolutely.
Yeah. Works better.
And there are people doing that in production, today. So that's
right.
That's not an uncommon thing. It's not the prevalent method because it is a more expensive process, and the powders are a little bit more expensive because they're narrower, finer cuts. But it's certainly technically sound, and it's being done every day.
But Dave, we covered a lot of stuff here, and I know in some cases we tried to make it sound a little bit simpler. So for those of you watching, if you got questions, you can call me, Bob, at 724-229-5791 here at Thermal Spray Depot, or drop me a line at bob@thermalspraydepot.com. And hey, Dave, what's your contact information if they want to come to you direct?
Yeah, if people need additional information about some of the technical things we talked about, or if we can help in any way to help you tackle your problem, you can contact me directly at 734-309-8645, or my email at info@surfaceflowtech.com. That's SURFACEFLOW.com.